heard a lot about imperative languages and Hoare-like logics to do with bug finding and incorrectness. But I'm going to talk about functional programming and types, so another outlier in this event. So of course, the core of a functional language is the lambda calculus. So we have there our abstraction, application, and variables. And for some more interesting examples, I'm going to add ADTs and pattern matching. The types that I'll be concerned with, we have our type variables, the arrow type for our ADTs and pattern matching. I'll also include constructor types and sum types. And I'll also add on a top type at the end, so all values will be a member of this OK. If you're unfamiliar with constructor types, they're a nice way to type our constructors. So nil, the empty type, is a constructor itself, and so it can be typed at nil. The list containing only one can be typed at cons nat nil, but of course both of these can also be typed at list of nat. Typing judgments, as I'm sure you all know, take this form for just about any type system that you're concerned with. You'll be proving judgments of this form, where we have a list of variable typings on the left, and then we have some term that we're interested in being typed on the right. We can then interpret this, at least informally, in this manner, where if we have that all of our variables sit inside their respective types, then our expression must sit in our B type or diverge. But of course, this doesn't tell the whole story and doesn't do everything we want, otherwise we wouldn't be here talking about incorrectness. So one of the simplest bugs that you can have is that the program just crashes. So one way that we can encode this is by saying that a given expression E is not in this top type OK. This is because if E does not evaluate to a value, then it must either crash or diverge. But clearly this is a negative statement, which doesn't look anything like what we already know. If we try and write this as an implication, we end up with this, which is closer, but we still haven't gotten into a form that we can use with typing judgments. So if we, again, take some general typing judgment from any type system, we can make some observations on some restrictions on this judgment that are stopping us from modeling this implication that we want. So the first is that only variable typings can occur on the left. We had an arbitrary expression being typed to OK on the left with our implication, but we don't allow that with our typing judgment. The second is a bit more subtle, but there must be exactly one typing in the conclusion. We wanted a false in our conclusion, which isn't a typing, it's a more meta value. So let's just relax these restrictions and examine the form of these judgments afterwards. So both of these forms can technically be summed up in the first one, but the second one is more interesting for bug finding and incorrectness. So as you can see on the left, rather than simply variables, we allow arbitrary expressions to be typed in the context. And on the right, we either allow some list of expression typings on the right, which may or may not be empty. Now it's great writing this down, but what do we actually mean by this? Well, let's look back at our logic. So again, if all of the expressions on the left are in their respective typings, then at least one of the typings on the right-hand side is in its type or diverges. And if there are no typings on the right, then there isn't a typing that can be satisfied, and so we have false. So let's look at some examples and see if we can actually see what we can write with this, see if we can model our desired implication. So the first example is a simple right-handed one. So we still have all of the theory and results over decades on correctness logic. This is simply a reminder on how you may use types to describe properties, more complex properties of a function. So here this is saying that if you give the map function a function that maps natural numbers greater than 3 to natural numbers greater than 8, and you also give map a list of natural numbers greater than 3, then it will apply the function to every element in the list, and it will produce you a list of natural numbers greater than 8. So for the rest of this presentation, I use quite simple types, but you can just as equally replace the simple types with more interesting properties. So example 2 actually uses our two-sided system to describe some reasoning that you may use while you're programming. So number 2 can be read as if x plus 1 evaluates to a natural number, then the identity function applied to x evaluates to a natural number. This is follows the natural reasoning that you'd have of if x plus 1 is a natural number, then x must be a natural number. The identity function simply returns the argument it's given, and so the identity function applied to x must return the must evaluate to a natural number. Number 3 gives us our first example of negative reasoning. So you can read this as if the empty list evaluates to a natural number, then false. That is, this is saying that the empty list is not a natural number. Now for a more clear example of bug finding and incorrectness. Fourth example says that if 1 plus the empty list evaluates to a value, then false, i.e. that 1 plus nil either crashes or diverges, but clearly doesn't diverge. And then number 5 follows very similar reasoning to number 4, but simply uses some pattern matching. But how do we derive or prove these judgments? Well, as usual, we use typing rules. So the typing rules at the top are standard typing rules that you can look up in just about any lambda calculus textbook. But we've sprinkled some deltas on the right-hand side, which are simply the typings on the right that you aren't interested in for this particular instantiation of the rule. The 2 rules on the bottom are some left-handed examples. So the first one is refuting that a constructor is typed at a given constructor type. Following through the reasoning, if you want to refute that a constructor with some arguments is typed at the correct constructor type with some types for its arguments, then as the constructor type, the outermost constructor is correct for the type, it must be that there exists some argument to this constructor that has been given the wrong type. The match L rule on the bottom, this rule has been both simplified and specialized. So there are most likely some cases that there may be ways to refute a typing for match that are not covered by this rule. However, following through the reasoning of this rule here, we look at the branch PS that would evaluate if match produced something of a successor, and we try and extract information from this branch about what the type of the free variable x must be. As in our pattern match, we have this free variable x in successor, and we just want to try and find what type PS requires that x to be. And then in the other two premises, we simply try and type E at the branch's type, but with the free variables replaced by the required types that we know. So, interestingly, if it may not be the case that E produces something of both types, so if, for example, E never produced something of type 0, you would be able to extract that information from the second premise and refute that typing. However, in the third premise, if E did produce something of shape successor, you wouldn't be able to refute that typing, and instead you would have to prove something in delta from the information that you can gain from the given typing. So we're going to take a slight side tangent and talk about a new arrow type, necessity, which will be needed for the left-hand rule for application. So this is how we write this necessity arrow, and we read it A only to B. Since it's an arrow type, we already have an arrow type, so let's compare it to something that we already have. So we have sufficiency on the left, which is our standard arrow type. We have the two rules where they have a nice symmetry in the premise where the E and the X have been swapped around. So if we go through the examples to try and build some intuition here, the first example of sufficiency, with lambda x dot 42, if you give it something of type nat, then it will give you back something of type nat. That is, if you wish to receive a nat from this function, it is sufficient to give it a natural number, but of course you could give it something outside of nat. With map f, if you give it the empty list, it will give you back the empty list. But of course you can expand the codomain of that type. If you give it the empty list, then it will produce the empty list, but the empty list is obviously a list of alpha, and so it can also be given this type. However, as we know, it would be incorrect to give map f this list of alpha to the empty list type. With necessity, we're looking more at pre-images than images. So with the first example, the head function, if you want to get something of type alpha out of this function, then you are required to give an argument of the shape cons alpha OK. Now, the OK is important here because the head function places no requirements on the second argument to the cons. With map f, if you want to get the empty list out, then you are required to give the empty list. However, we do also allow elements from the domain of our arrow to not map to the codomain in a forward reasoning style. Similar to how in sufficiency, we allow elements in the codomain to not be mapped to from our domain. So with map f, if you want to get the empty list out, then you are required to give it something of list A. But this type is not the most strict type that you could give it. But it would be, for our last example here, it would be incorrect to give the lambda x.42 the type nat only to nat, because there is no requirement by this function for its argument to be a natural number. As I said before, you can give this the empty list and it will still produce a natural number. So now we can return to application on the left. So you can see here that if you wish to refute that an application has a given type, then first you need to show that the function part of that application requires that the argument, if you want to produce a B, the argument is required to be in type A. But then you also show that the argument that you're actually giving it is not in this type A. And so now that we have application on the left, we can actually show interesting examples of finding bugs. So the classic would be giving the empty list to head. So the head function, if you want a value out, then you have to give it an argument of shape cons OK. And of course, nil is not a cons-like thing. And thus, we have proven that head of nil does not evaluate. That is, it doesn't reach a value. So, in conclusion, by using this two-sided framework to our typing, we maintain all of the results over the past decades on well-typed programs by typing on the right, as we always have. However, we can also, if we can type a program at OK on the left with no conclusion, then we can prove that it will not evaluate to a value. And as this is a special case with practical applications, we've decided to call this particular case that we say that E is ill-typed. And thus we can have the tagline, ill-typed programs don't evaluate. Thank you.
Thank you, Charlie. It's never easy to be the last talk of the day. Thanks again. Any questions for Charlie? Patrick.
I have not understood how you handle recursion, because you have no recursion operator, and your type system cannot type combinators.
So in the full paper, we do have fixed points. So we do have recursion, and that does play well with the system. I've just not included it on the slides for simplicity. So we can still type fixed points on the left. Applications and fixed points are sort of a special case. You can create a specialized rule for them, but they involve inventing a value to show that its property is incorrect. The way that we actually use it in practice is through a axiomatization of disjointness between two types. So if you want to refute that, for example, head is a nat to nat function, then you instead affirm that it has some other type that is disjoint from nat to nat. And then a similar result for similar rule for fixed points.
You don't have to prove either non-termination and termination to conclude? That's surprising.
So for call by value, you don't have to talk about termination at all. For call by name, you do have to talk about termination of various things, and so the call by name system is significantly weaker than the call by value system. But for a call by value type system, you don't have to talk about termination.
Are there many programs in the middle that neither are well-typed nor ill-typed?
Yes, there are. So there are programs that are neither. That is almost certainly how we're getting around talking about termination. Interestingly, there are actually programs that sit in the intersection that are both well-typed and ill-typed, and they would be divergent programs. So the fixed point of the identity function is both well-typed and ill-typed. I don't know if we have a proof for it, but I believe that only divergent programs can sit in its intersection.
You mentioned using it in practice. Do you have an implementation of type checking or type inference or anything?
So we have type inference, an algorithm for type inference. It hasn't been implemented, but there is an algorithm in the appendix for type inference. It uses, so it's completely automated and uses standard techniques. There is very little interaction between the two sides. But as a given term does not have a unique typing, we work with sets of types, or in the case of the actual algorithm, sets of judgments, because you need to keep track of whether a given type is proved on the left or the right. But we do have type inference for the system.
What do you understand as go wrong? Because if you over approximate, you divide by 0, it doesn't go wrong. And when you under approximate, you divide by 0, does it go wrong or not?
So we define go wrong by does not evaluate to a value.
Okay.
So as for under and over approximate, the necessity arrow that I've been talking about is roughly necessity logic in the whole-like logics. So it's a functional representation of the necessity triples.
Okay, let's thank Charlie again. Oh, well, is there another question? Okay.